Hello, my name is Shivdath. Today we're going to be looking at various areas of math, the different fields of math, and how they come together, how they overlap, how they integrate. When somebody tells you they're a mathematician, they could be studying and working in various different fields, which, although have a similar flavor and are related, are also very different. So today we're going to look at the various fields of math, how they connect together, and what really the overall overarching structure is. Alright, so very broadly, and this is just a really broad umbrella to look at, but we'll definitely go into more details afterwards. But very broadly, math can be divided as follows. There is, and this is in no way by order of importance, there is number theory, there is geometry, there is algebra, and there is analysis. So really, as you get into higher math, all it does is it takes the math you did in high school, and perhaps even before high school, middle school, apart from analysis, which is really just calculus, and it just makes it more and more complicated. You go deeper and deeper and deeper. It's the same thing, the same problems. You get deeper and deeper and deeper into them, and from there emerges a whole complex range of different subfields. But really, it's the same thing. Arithmetic, 2 plus 3. When you first learn to add and subtract and multiply and divide numbers, that's really nothing but number theory. Number theory is really arithmetic. It corresponds to our notion of quantity. So why math is so applicable to so many different fields, and really permeates our lives in every dimension, whether it's coordinating airplanes, or running a computer system, or in finance, just wherever, describing the physical world. It's just because math takes common sense, very simple basic quantities, and analyzes them very rigorously. So arithmetic, number theory, really corresponds to our idea of quantity. There's geometry, which corresponds to our idea of space. Every high school kid is familiar with geometry, triangles, circles, studying their properties. There's algebra. Again, every high school kid is familiar with having that variable x which he solves for, or manipulating algebraic expressions. But what algebra really does, and you see this as you get into study, things like linear algebra, abstract algebra, is it really makes sense of the notion of structure. So to understand the structure, the inherent structure, the meat of a system, how it fits together, which will give you a better understanding of the entire set or class you're dealing with. And finally, analysis, which deals with the concept of change. So analysis is really nothing but a more advanced form of calculus that we do in 10th, 11th, 12th grade, depending on where you're studying. But as you can see, these really are the basic notions of our everyday experience. There's change, there's structure, there's space, and there's quantity. And just kind of try and think of any space-time. The world we're living in is 3 dimensions of space and 1 dimension of time. That time variable will come and change. When something's changing, it's changing. It could be changing with respect to anything, but as one example, it would be changing with respect to time. Space, those 3 dimensions that we're dealing with. Then within that space-time, we humans build various things and put them in, and really to understand their structure, what their underlying basis is, that's what algebra comes into. And then there's always that question of how many, how much, how long, these questions keep troubling us. That's what quantity is, and that's what number theory deals with. So this is a very broad overview of pure math. Pure math deals with these inherent kind of structures of reality, these facets of everyday life and tries to make them rigorous. Now, apart from that, there's also logic, which basically looks at the foundations of mathematics and asks a lot of philosophical questions. For example, how are we, we build axiomatic systems, we do this, we do that, but how are they justified? Is this okay? Questions like, is mathematics invented? Is it discovered? Is it kind of existing out there and we just discover it? Or is it a figment of our, our imagination, our brains, electrical signals being fired in our brains? Or just questions on the validity of methods used in each of these fields is basically handled in logic. So it's really the foundations of mathematics that logic deals with. And finally, there's applied math, which looks at applications of mathematics to various different fields. Now, there are various ways of classifying, different areas of math. Like one glaring omission which you may feel is, just kind of screaming out of the page is what happened to probability? Where does that fit into this? Or just things like graph theory. Graph theory is kind of like structure, right? It's understanding connectivity, but where does that fit in? Is it applied math? Kind of, yes. So there is a lot of overlap going on. Yes, graph theory would kind of answer that structure question. It's also an area of applied math. And the whole discrete math, which I could really put as a separate subset, which deals with, combinatorics, probability, graph theory, things like that, where you have discrete components and you do a lot of mathematical analysis on that. But I'm just going to club that all under applied math for now, and we can take a more detailed look at it later. So take a while, pause the video and internalize this division, and then we'll jump into a little more detailed discussion of each of these. Definitely not very deep, but we'll look at some of the main ideas, some of the main problems they deal with. Alright, so let's start off with logic. The very foundations of math. And this is important since all the math builds up upon it. So basically there are four areas of logic which are really called the four founding pillars of mathematics. There is, there is set theory. There is recursion theory. There is model theory. And finally, there is proof theory. Now, very quickly, set theory is basically the study of sets, and it's amazing how often the concept of a set comes up in math. It just basically is ubiquitous. It comes up everywhere, because if you think about it, most things we're dealing with really are sets. The integers are a set of some kind of numbers. The rational numbers are a set of some kind of numbers. So, when we're dealing with combinatorics, we're always dealing with a set of objects. So set theory comes up everywhere, and it's really kind of essential and integral to the foundation and the understanding of math, because a lot of operations which we can perform on, mathematical operations really are performed in sets. Unions, intersections, these simple things which you studied and heard of, really they kind of describe combining quantities and manipulations that we can do. Recursion theory, which is also called computability theory, is basically, it's really looking at various other aspects of logic. Think questions about computability, for instance. We're not going to delve deep into any of these, but very quickly, model theory. Apologies for the L. Model theory basically is it studies structures like groups, rings, fields, which we'll come to in a bit when we discuss algebra. But it studies classes, structures which are defined by certain properties of this, using using logic, using things like set theory or logic. Logic involves things like just questioning propositions. If A, then B. not A, then dot B, things like the contrapositive, just normal things that everybody would agree make sense. And then finally, proof theory basically looks at proofs as these objects, and kind of by making connections between those objects, it kind of looks at what makes a valid proof, and different methods of proof, for instance. It's much more complicated than that, but that's really a very high level description of what proof theory is about. So for example, the various types of proof. There's proof by contradiction, so that would kind of have a chart with saying, I assume not this, and then kind of reach a contradiction from that, and so on. So these are the 4 pillars, but there are really kind of various other forms that logic is studied in. Category theory is an important one, which basically kind of constructs these things called categories, which are basically a combination of objects, functions between those objects, and this idea of a composition of functions. So if you had an object A, B, and C, and let's say there were mappings of functions f from A to B, so when you apply the function f to A, you get B. When you apply the function g to B, you get C. But is there a way to go from A to C directly? What would that function be? That would be nothing but the composition f of g, meaning you apply f on A, and then you apply g on that result, and you get C. So this function is f of g, and this whole thing would be a category. And it turns out, it's pretty straightforward and makes sense, but it turns out, studying a lot of math in the form of categories makes proofs much more simple and makes results much easily available to see. Things that may be much more complicated, and things one would otherwise be likely to miss show up much more clearly. Apart from that, there is theoretical computer science, which again has various forms. There's information theory, which looks at basically the quantification of information and how that makes sense, how that's possible. There is complexity theory, which looks at algorithms and their performance times. So for example, an order n squared algorithm, while it may get a small problem done when the input size n is small, it blows up very quickly. And changing, if you could find it quicker, say an n log n algorithm, that would really happen and make things much faster as n gets large. There is computability, which looks at the limits of what a computer can do, and for different models of a computer, of course. But universally recognized model is a Turing machine. It's a simple machine which kind of reads the state. It has a head. It can store a certain state, and it has a table with a set of rules. Kind of limitations on what a computer could do. So, for example, the halting problem, like could a Turing machine decide whether the program will halt, and the answer turns out to be no. It's something that's undecidable. So that's really that's kind of really a broad overview of logic. We have the 4 pillars. Set theory is probably by far the most important. It shows up all the time. A lot of problems in mathematical logic. Bertrand Russell, for example, came up with a few paradoxes that arose from set theory, and which kind of were ultimately put into perspective by Gödel. His idea that we discussed in another video of incompleteness, basically a system cannot, a theory or a system cannot be both consistent and complete at the same time. So problems like that are really deal with mathematical logic, and are important because they're inherent to the foundations of logic. If it turns out our foundations are incorrect, then there's no point in proceeding. For example, Hilbert had this problem of trying to put mathematics on a sure foundation by having this set of axioms from which everything could have been proved to be false or true, and any statement could be false or true, and should also be consistent. Well, Gödel proved, gave a decisive blow to that idea by showing that no axiomatic system can be both consistent, meaning it doesn't have internal contradictions, and complete, meaning there'll always be, and consistency is something we always want, so let's keep consistency, but then it won't be complete, and otherwise In other words, there will be statements that you can't prove are false or true. You just can't say anything about that. So that's a very broad overview of logic. And let's move on to algebra. Alright, so if you remember, I talked about algebra as being kind of quantifying the notion of structure. So how did the idea of algebra emerge? Now this is a little different to the algebra we do in high school, x squared plus 5 equal to 3, something like that. But it really is also very similar. For example, a lot of algebra is studying roots of equations like this. But I think integral to algebra is the idea of these concepts of these classes, like things like groups, rings, and fields. Now, what exactly are they? Well, consider the integers, which often represented by this funny-looking z. The integers have certain properties. Think about two integers. If you add them together, you get an integer back, right? If you multiply integers together, once again you get an integer back. But what if you divide integers? You don't get an integer back. You can get a rational number, like 1 divided by 2 gives you half, which is not an integer, right? It's kind of, you step outside that set. So kind of defining these sets, these sub-universes that you can't escape, that have certain rules on them, addition and multiplication, that have identities. Defining these structures is what algebra is all about. So let's really look at what groups, rings, and fields are. So groups are structures like the integers. And the integers is a great example of a group that basically have this operation. Let's call it addition, right? We'll ignore multiplication for now. So the integers under addition form a group. And the idea is that we want them to be closed under addition, meaning if you add two integers, you get an integer back. You don't escape that space. They should be associative, in other words, a plus b plus c equal to a plus b plus c. It doesn't matter which two you perform the operation on first. They should also basically have an inverse. So a will have, there will always be negative a in the set of integers, b will have negative b. And inverse is just what gives you the identity, and the fourth property is the identity, which when you perform the group operation, which is addition for us, on that integer, you get that integer back. So a and the identity here would be 0, exactly. So a plus 0 gives you 0 back. So, so it's really closed, associative, we have the identity, and we have inverses. Let's look at a ring. A ring, the integers are also an example of a ring. And what a ring is it's similar to a group, except that it has this additional property, which we'll call multiplication. So a ring is nothing but an abelian group. And what is an abelian group? An abelian group is nothing but an abelian group under multiplication. And abelian just means that a into b equal to b into a. So it's a group under both addition and multiplication. But it also has the property that it is distributive over the two operations. In other words, a into b plus c equal to a into b plus a into c. So that's what a ring is. You see it adds a little more structure, it adds this other operation called multiplication. And finally a field, which is nothing but a commutative ring. That has inverses. In other words, if you had a and b, and you did a divided by b, right? You don't get an element which is in the group or the ring. But a and b would also be in the field. So the rational numbers form a field. You can call the rational numbers Q. The rational numbers are a very good example of a field. So somehow, we're kind of adding more and more structure. These three kind of show up all the time in algebra, and they're really kind of inherent to different areas of algebra, and in fact show up all the time in other areas of math too. Set theory, for instance, and so listing them here, they are really important. Now, I should also mention linear algebra, which basically looks at spaces, vector spaces. Now, you know from high school, maybe physics, that a vector is, this arrow kind of thing which has a direction and a magnitude. So it has some angle theta, which gives it a direction, the x-axis say, and it has some magnitude, say it's of length phi, right? Now just imagine all possible vectors that you could draw. Is there some, subset of vectors that could generate all those vectors if combined in various linear combinations? For example, say I had this vector and I have this vector, right? If I combine them, I get something like that. So in other words, I really don't need this. I need these two, and I can already generate that. So the generating vectors are said to form bases, and all other vectors that you can form from them, if you look at that whole space of vectors, including the bases, that forms a vector space. There's some rules, for example, there are some more rules, but the very kind of basically that's what the idea of vector space is. And linear algebra is really the study of vector spaces. Now, I should mention that the idea of structure is, kind of emerges in a lot of other areas of math. We talked about graph theory, right? Which is looking at networks and connectivity and basically the structure of a system. For example, you can really tell the structure of a social network, like Facebook, very well by studying graphs where the nodes are individuals and connections would mean there's a connection between them, they're friends or whatever. There is combinatorics, which looks at the kind of inherent structure of a system by looking at ways you can enumerate it. So if I give you numbers 1 to 10 and I tell you to print out all permutations of that, that's really looking at the inherent structure and how all enumerations under a set of rules. Order theory, which basically looks at a set and kind of gives you some order operation for the elements. For example, for numbers, you can have the orderation greater than, less than, which impose some order on that system. All these different areas of math impose structure as well. And I mention them because kind of we're really dealing with structure, even though they may not be algebra per se. But this is a really broad overview of algebra. You'll see algebra, emerging in various other fields of number theory and geometry, just to name a few. But and pure algebra itself. But I think groups, rings, and fields are these important structures that just show up so frequently and are so applicable to so many different areas of human study. For example, groups. Group theory comes up when you're studying the electron spin in quantum mechanics. People often describe spin as being the rotation of a ball. You can visualize it that way, but it really isn't. It's really just an abstract property that emerges from group theory. Similarly, group theory is often studied and understanding the structure of a Rubik's cube, which can give more efficient solutions. It's often when you look at a group theory article, you'll see that picture of the Rubik's cube drawn beside it, since they go so closely. And fields and rings come all the time. Anyways, let's move on to number theory. So if you guessed the number theory, remember we said it's basically making sense of the notion of quantity. But if you thought that number theory was the study of numbers, well, you're partly right. But number theory is really the study of integers, right? Now, I'm tempted to say that number theory is not the study of things like rational numbers and not the study of, say, real numbers, and it doesn't study the number line, for instance. It studies parts of it. It studies the integers and things you can do with it, but not really real numbers. That comes under analysis, and really, analysis, real analysis, studying the real line. You add the y-axis, you get complex analysis, and so on. But that's a bit of a specious argument because really everything comes from the integers. You have the integers, right? They belong to the rational numbers, which is nothing but integers of the form A, rational numbers of the form A by B, when you divide two integers, which belong to the real numbers. Real numbers include numbers that you can't write in the form A by B. Pi, for example, right? We commonly write it as 22 by 7, but that's just an approximation. It's actually a non-repeating, non-terminating decimal. And the real numbers can be constructed as the kind of limit points of Cauchy sequences. So you have this infinite sequence of rational numbers, and it converges to this number called a real number. So pi would be, there will be an infinite sequence of numbers of this form, which converge to pi. I mean, you can get closer and closer. They never actually reach it, but you can get closer and closer and closer. And this concept of never actually reaching, this is something that would be studied extensively in logic, in mathematical logic, to make sure our notions of making this getting infinitely close and something existing makes sense, and mathematical philosophy. The real numbers themselves are a subset of the complex numbers, where you have a real and a complex component. E to the power b, c over d, and that means it converges. Complex numbers are of the form x plus iy, where you have that imaginary component, and complex numbers themselves belong to more exotic forms such as quaternions and octonions. So very, very quickly, what exactly are the quaternions and octonions? We're not going to get into deep discussion, but the quaternions can really be written of the form a plus bi plus cj plus dk. So you have these ijk kind of axes, you can call them. And it actually, this is used a lot in physics to study three-dimensional rotation, with ij and k corresponding to the three dimensions. And the quaternions form a group under the operation of multiplication. So, for example, you have I into j is equal to k, j into I is equal to negative k. And when you define the group operation, define the multiplications, they actually form a group. And it's very interesting used in studying 3D rotation and a group of rotations. Octonions are basically all linear combinations of E0 to E8, which are vectors. And again, groups and group theory, algebra, structure, we see already the structure coming in. We know that the integers are a group, the rational numbers are a field, and so on. So even though I say that number theory is the study of integers, it really is indirectly the study of everything, since everything really emerged from the integers. As the famous Chronicle quote goes, God gave us the integers, all the rest is the work of man. Basically all we need is the integers to start, and once we have those, everything is constructed out of them. Introductory classes in real analysis will show you how to construct the real numbers out of rational numbers as infinite sequences of infinite Cauchy sequences. There are other ways as well, Dedekind cuts, but that would be for another day. Alright, so number theory is really a study of integers, and in particular it's a study of prime numbers, which are really, really fascinating integers. The numbers 3, 5, 7, 11, 13, and so on, which don't have any, are not divisible by any other integer less than them. Any other integer for that matter. And why, some other problems come up in number theory as well, the concept of infinity, which would also come up in mathematical logic. But the different notions of infinity, different orders of infinity, which cardinality, we call it cardinality, different orders of infinity. And it turns out there are actually infinitely many orders of infinity, which is kind of really mind-boggling. But just to give you a taste of what it's like, let's look at countable infinity versus uncountable infinity. So countable infinity is something you can count. For example, you can actually list it out, or map the integers to to that list. That would be something which is countable infinity. So, you know, all the integers, for instance, I know they're infinitely many, but I also know how to count them, right? Because you tell me an integer to get to, and I can get to it. You tell me to go a little further, I can keep going further. Sure, I'll never reach the end, but I know how to proceed, right? There's a mapping between the integers and the integers in this case, a trivial case. Similarly, the number of rational numbers is a countable infinity because I can kind of map, I won't do the mapping here, but I can map the integers to that. On the other hand, the set of real numbers is uncountable. And why? Well, supposing this is Cantor's famous diagonalization argument. You know, supposing I did have a map, 1 corresponds to this, 3 corresponds to this, 4, 0, 1, and 2. And I'm only going to write zeros and ones for now. Right? Supposing so this went on, and supposing I told you, I mean we can't see the end, but supposing I told you, here I've listed out all the integers I've listed on a map for all these numbers 0 and 1, and you know, you could imagine like this being a decimal point here to give you real numbers. These say these don't finish. These go on and on and on. Supposing you did tell me you have this list here, I could always construct another element, right, to show you, which would basically prove that your list was not complete. And the way I would do that is I would take the first element in your first number, the second in your second, the third in your third, and so on, forming really a diagonal, and I'd flip it. If it was 0 here, I'd make it 1. If it was 0 here, I'll make it 1. If it's 1 here, I'll make it 0. That number is guaranteed to differ from each of these numbers in at least one place, the place you flipped it. In other words, it couldn't exist in this list. So you just create, even though you told me you listed out all possibilities, you didn't, because I created something else which was not in there. So you know, that's an uncountable infinity. And this kind of surprising result is that there are infinitely many orders of infinity. But let's not go into any more detail into that and get sidetracked. So you know, very famous number theory problems are the twin prime conjecture, which basically holds that there are infinitely many twin primes, and twin primes are, you know, prime numbers separated by whose difference is 2. For example, 3 and 5, or 5 and 7, or 11 and 13, 17 and 19, and so on. Similarly, the Goldbach conjecture, which basically states that any even number is equal to the sum of 2 primes. Now, this has been proved to hold true for 10 to the 18, was it, or 4 into 10 to the 18? But you know, it hasn't been proved true categorically for numbers higher than that. And now I should mention that, so you know, these are the kind of prime number problems that number theory often looks at. Now I should mention that there are really two kind of broad subfields of number theory. There's analytic number theory and there's algebraic number theory. And kind of very briefly and intuitively, analytic number theory uses methods from analysis, one of those main domains of math that we looked at, and that we're going to look at further. And algebraic number theory looks at algebraic methods of studying number theory. We already looked at a bit of algebra. So analytic number theory would, you know, kind of involve problems like those two we looked at, the Goldbach and the twin prime. It also, the Riemann-Zeta hypothesis, which we may go into in another lecture, but if you've heard of it, very famous hypothesis is also, you know, problem analytic number theory. Well, you know, algebraic number theory really kind of looks at algebraic ways of dealing with a number theory. For example, an important notion is that of an algebraic number, which is the root of a polynomial with rational coefficients. So kind of just as those prime numbers were the bread and butter of number theory, which is really what number theory kind of deals itself with, algebraic number theory really, you know, algebraic numbers are integral to them. Analytic number theory will, on the other hand, you know, look at, it'll look at ideas of estimation, so finding orders of magnitude, or density. In other words, finding when things are when numbers are going to approach some limit or get closely clustered together. These kind of problems would be under the domain of analytic number theory. Algebraic number theory looks at it from a much more algebraic perspective. More recently, there's been a burgeoning of various other fields of number theory: probabilistic number theory, numerical number theory, combinatoric number theory, but we're really not going to get into those now. But I mean, these are all very, very valid fields and plenty of people working in them. Moving on, we're going to take a look at geometry. Which basically makes rigorous our notion of space. Now there's Euclidean geometry, which was really the axiomatic geometry that Euclid developed, his 5 postulates, and he derived all simple plane geometry that high school students deal with today, studying triangles and circles and their properties, etc. Then there is analytic geometry, which is really Cartesian geometry, which the French mathematician and philosopher René Descartes introduced, which combined algebra and geometry by dividing the plane into making it have the x and y axes with numbers on it. So from there we kind of married algebra and geometry, and that was a big breakthrough because the first time two algebra and geometry, two really disparate fields, kind of became one. We have then we move on to non-Euclidean geometries, which basically do not take the 5th postulate that parallel lines never meet. So for example, if you look at the Earth, right, longitudes are parallel lines, but they actually meet at the poles. So in that vein, Riemannian geometry is a great example of a non-Euclidean geometry which the German mathematician Riemann developed, which was used by none other than Einstein extensively in his theory of general relativity, to describe the structure of space-time and its warps which are caused by massive objects inside it and the propagation of gravity waves through it. Then so analysis enters geometry in differential geometry. Which basically was was also used extensively in general relativity, but it basically looks at geometric structures and tries to apply analysis techniques of integration and differentiation, made more rigorous of course, to solve problems. So for example, things like finding the derivative will give you the kind of rate at which the slope is increasing or the surface is increasing, finding the curvature by again calculating differentials. All this is differential geometry. And then there's algebraic geometry, where algebra makes its advance into geometry, where we study geometric problems using algebraic techniques. So central to algebraic geometry is the idea of algebraic varieties, which are basically a geometric description of the solution set of a certain equation. So just as a parabola is a solution to y equal to x squared, right? That's a geometric answer to this algebraic question. Really what algebraic geometry does is takes this and does it for much more complicated shapes and describes algebraic varieties, and it has a lot of applications to number theories and so on. Then I'm going to get to a very important branch later which is connected, but we have fractal geometry. Fractals are basically these structures that have There's kind of infinitely repeating patterns, and I will make another lecture on it. But you know, a very example is the snowflake, the Koch snowflake, where you have a triangle, right? You make triangles on each of its sides, and then you repeat that process infinitely. So you take these two sides, make a triangle, make a triangle, make a triangle, and if you keep repeating it, you get what looks like a snowflake, and it'll look like a snowflake even more accurately as you repeat the process. My artistic skills are not very good, but you get the point. You know, fractals show up all the time, and what's amazing is no matter how many times you magnify, you see the same structures reappearing, and you see it so much in nature. For example, a leaf, right? You have 1, 2, and then you just keep repeating that pattern. You get what really looks like a tree. So it really seems that, you know, nature kind of works through fractals, but no more on that. We'll get to that in another topic. But the idea is that they have fractal dimensions. So like you could have a 2D structure, you could have a 3D structure, and then you can have a 2.5 dimensional structure where fractal dimension comes in. Then we have discrete geometry. And I'm going to club a few of these together. We have basically discrete geometry, convex geometry, computational geometry. So discrete geometry looks at discrete geometric structures, a set of points, and, you know, perhaps ways of connecting them. Convex geometry studies convex sets. Computational geometry is really at the intersection of computer science. It looks at geometric answers to solving algorithms efficiently, developing efficient algorithms, and you know, usually in computer science you're dealing with discrete data sets, and so that's how computational geometry enters that. Finite geometry is another field. I'm not even going to write it down, but that's really related. And finally we get to topology, which really could be a separate field, but really it's geometric enough in nature, since it really is dealing with the idea of space. And what topology can really be described as is a coffee and a donut, a coffee cup, a mug, and donut being the same. Because really you can map one to the other, you can transform one to the other without causing any breakages. You have a smooth mapping, continuous mapping from one to the other. And the idea is that the reason is because they have the same number of holes in them. The coffee cup will have a hole in its handle here, and the donut has a hole in the center. But you wouldn't have to rip the donut or the coffee cup to map one to the other. In other words, there's a smooth mapping, and there's a smooth inverse mapping between them. But if you wanted to convert a donut with 2 holes into one of these, that could not be done topologically through a smooth mapping, and so they would not be topologically equivalent. In topology itself, there's just various kind of sub-areas. There's point set topology, you know, which deals with we're really with the properties of a topological space. There's set topology, which kind of takes in set theory. There's algebraic topology, which looks at algebraic approaches to studying topology. The differential topology, just like we have algebraic and differential geometry, we have algebraic and differential topology, and you know, the list could go on. But this is really, again, a very broad overview of geometry and the different areas in it. And without further ado, let's get to our last pure math topic, which is analysis. Which, as I mentioned before, makes rigorous our notion of change. I don't know, I've always thought of analysis as really the study of functions, and differential equations, which can be regarded as a subset of analysis, whereas is what deals with change. But anyways, since functions are not perhaps inherent to what we see around us, let's just call it change, because, you know, a derivative is a change, an integral is also dealing with a change. So analysis is really nothing but the high school we see. high school calculus that you all have done, made very rigorous. So instead of actually being told to take the integral or something or differentiate something, you'll be made to do more general proofs, which kind of really puts things on a much stronger footing. Even things like constructing the real numbers as infinite sequences, as the limit of an infinite sequence of infinite Cauchy sequence of rational numbers is also a problem one studies in introductory analysis. So really this is calculus that we do in high school, made rigorous. After the normal calculus that most people do in high school, single variable, comes multivariable calculus, which really is calculus in two variables. So if you have a function, if you want to take the derivative with respect to x of a function, x squared plus y squared plus 2xy, how do you do that? Well, this is actually a partial derivative, because you're only taking the differential with respect to x. Similarly, you can take a partial derivative with respect to y, and similarly you can integrate with respect to y with respect to x or whatever function you're dealing with. And the order is important. Sometimes you can change the order up easily, sometimes it's a little more tricky. So that kind of, it's really the same thing, but there's slight variations, and then there's some additional theorems, Gauss, Stokes, and this has numerous applications to physics, shows up all the time in electricity and magnetism, and also a lot of geometric applications. It's multivariable calculus is very geometrical in flavor. We have complex analysis, which basically, real analysis first, which basically looks at analysis of functions in a real variable. We go into more complexities here with Hilbert spaces and Banach spaces, but actually even fractal theory emerges from that. But let's look at complex analysis, which usually tends to be a little easier. Again, used widely in physics, and also has a very computational flavor in many points. Basically, it looks at analysis of functions in a complex variable. So complex functions, the rules, just as the rules for differentiation and integration are slightly different here, they're also slightly different here. The exact same, it's not the exact same rules that you normally use in normal math. And finally, there's functional analysis, which basically looks at analysis on infinite dimensional function spaces. And I should also probably mention differential equations, which arise from analysis, which kind of used widely in physics and used anytime we're dealing with any change at all. It's kind of solving for a variable based on its rate of change with respect to another variable. So that's really what analysis is about. We see it entering number theory and analytical number theory, geometry in differential geometry, shows up all the time, in wide varieties of applied math as well. But in a nutshell, that's really what the whole field of analysis is about. And moving on to our last topic, which is going to be applied math, which has a variety of subfields. We won't examine them exhaustively, but we'll kind of make a list of some of the important ones and take a brief look. So I hope you had a chance to internalize this. So we have applied math. So like I said before, one really important area in applied math is discrete math, and it really could get a whole topic by itself. Discrete math, which deals with discrete kind of components and does mathematical analysis on them. Things like graph theory, some areas of algebra as well. Group theory would come there. Set theory could be involved in that. Probability, combinatorics, those all come under the framework of discrete math. In discrete probability, that is, when you have discrete events and you're not looking at continuous distributions. But let's try and list down some of the areas that we have probability. We have, this pen's not good. We have statistics. Gotta rewrite this. Probability. Statistics. We have mathematical physics. You know, math shows up in physics all the time, but in particular, there's a different branch of math called mathematical physics, which we'll look at in a minute. There's mathematical finance, mathematical economics, mathematical biology and chemistry. There is, let's see, what else is there? There is control theory. And am I missing anything? There is cryptography. There is optimization. There is famous game theory. What else is there? There is numerical analysis, fluid dynamics, to name a few. So let's kind of go very quickly over these. Probability, looks at, again, it really, when I was mentioning facets of our everyday life and math, trying to quantify that, probability is what really quantifies the idea of uncertainty and risk. So, it shows up everywhere in finance. Whenever there's risk involved, some uncertainty involved, and we want to calculate the odds. There's discrete probability where you have discrete events, and also continuous probabilities where you have these continuous distributions. Shows up in quantum mechanics all the time, where you have an electron which really is not discrete. It can't be at one, but it has a certain probability of being in a region of space, and you integrate to kind of get the probability of that entire region. Integrate the probability density function. And probability actually turns out to be really closely related to analysis, since one is going to be carrying out integrals all the time of the probability density function. Statistics, basically, again, gathering information and kind of making decisions on the basis of that. But what's the difference between statistics and probability? Well, statistics seems more empirical, probability seems more theoretical. If you're thinking along that lines, that's really kind of correct. What statistics does is it takes samples, and on the basis of those samples, it tries to make inferences about the more general population. Whereas probability goes the opposite way. It has data, it has information about the entire system, and from that it tries to get information about a particular event. When a particular event is going to occur based on kind of an overall bird's eye view description. So they're really kind of going the opposite way. Probability starts from point A, tries to get to point B. Statistics starts from point B, tries to get to point A. Mathematical physics, again, math shows up in physics all the time. We talked about linear algebra being the basis of quantum mechanics, group theory, being used in making sense of electron spin, and just differential geometry and general relativity analysis just pops up everywhere. So mathematical physics is really a developed field. Probability itself shows up in statistical mechanics extensively. There's no shortage of example of areas of physics where you use number theory is being used too now quite a bit. Mathematical finance deals with things like just problems of optimizing portfolios, pricing derivatives, and really those are the two different broad categories. Derivative pricing, called Q, because they use the risk neutral rate Q, and portfolio management, which is really called the P word, because they're not using risk neutral probability. Mathematical economics, again, economics uses math to a great extent. Real analysis shows up a lot. For instance, biology and chemistry, math is used extensively in studying population dynamics in biology and chemical reactions. There are various kind of models proposed, formulas proposed for this. Control theory is basically looked at studying dynamical systems that we discussed earlier, but where you have some control to the inputs. So you kind of decide how often you want to turn an electrical signal on or off, etc. It's used extensively in electrical engineering. Cryptography, the basis of a lot of computation and a secure transfer of data from one party to another, so that if a third party intercepts the data, they won't be able to make sense of it. RSA, which is used so widely, is really essentially a cryptography technique, and cryptography has a lot of deep ties to number theory. If a good algorithm for prime factorization is found, that would kind of render useless a lot of our techniques currently in use today, for example, RSA. Optimization, another very important topic, really pertaining to daily life, where you want to maximize profits or minimize costs, always optimize, and it's really seen in operational research and financial engineering. Optimization, there are various techniques. In multivariable calculus, you look at Lagrange multipliers, and you use that to kind of find the maximum minimum. In simple calculus, you take the derivative and set it to 0. You take higher order derivatives to find out whether it's a maximum or a minimum. Game theory, again, very interesting, very popular with the mass media, where different scenarios and setups can be looked at as a game, and we assume that opponents are rational, and we assume the best play happens, and we try and come up with the best outcome. And there are a lot of paradox kind of scenarios where it would be in the best interest if the players could cooperate, but playing rationally would tell them to be greedy, and they don't cooperate, and they all end up with a worse outcome. We will study game theory in another topic. Numerical analysis actually studies numbers rather than algebraic manipulations of symbols that we see so commonly in math. It actually does approximations with numbers. And finally, fluid dynamics, which I guess could be clumped in mathematical physics, but it's really more of an engineering topic, which is to study the motion of fluids, liquids, and gases, through study their motion, whether it's through a pipe or the motion of air passing over an airplane's wing or what have you. So this is a pretty kind of broad overview of applied math. I've clumped in some topics like probability that really may deserve a separate section for themselves. But it's interesting to see how so many diverse areas of math come and are applicable to so many kind of problems that we deal with in our daily lives. And how math is so ubiquitous and shows up in just so many varieties of problems. And it really seems that the reason it does is because it tries to quantify and make rigorous these common sense, basic notions of space, time, change, structure that really are kind of inherent and basic to our experience of experiencing our world around us. I hope you enjoyed it. Thank you very much, and this should give you a really good broad overview of the different areas of math and how they're used in problem solving. Thank you.